Yeah, so I think we can start now, so people will keep joining in, maybe whoever has taken a break. So in the next session we have Dr. Vivek Seshadri. He has done his PhD from computer science in CMU and is currently a senior researcher at Microsoft Research. So today he will be talking about DRAM architectures, design and research opportunities. So over to you, Dr. Vivek.
All right, yeah. Thanks, Vishwesh, and thanks, Professor Madhu, for setting up the stage for the DRAM microarchitecture stuff that I'm going to present. So in the previous lecture, Professor Madhu covered sort of a top-down view of how DRAM is integrated into today's systems, with lots of details on the memory controller, and how the memory controller schedules different commands to DRAM. And like you mentioned, DRAM essentially today is more a device that receives commands from the controller and then executes on those commands. So in this lecture, what I will try to do is take a bottom-up approach and see how a DRAM cell operates at an individual level, and how we take that individual cell operation to essentially arrive at the design for the DIMM that we have today. Right. So before we begin, I just had these two empty slides with sort of an interaction with the students. So can the students actually type out in the chat, like what are some memory devices that we use every day? Yes, we have one answer already, like DRAM. But yeah, maybe you can just type out other things that come to your mind in your day-to-day life. What are the memory devices that you use? Pen drives, flash drive, hard drive. Brain, interesting. How about within? I mean, so we are looking at things outside of uh, a computer that we probably see. How about inside a computer chip? Registers, ROM, SRAM, cache. Cool. All right, great. Yeah. So as you can see, we have these plenty of different types of memory devices, that we use every day. And there's one natural question, why do we have so many different devices? Why is there not a single device that we use, for everything? So that brings us to my next empty slide, which is, what do we want from a memory device? So we have listed, so many different things, and you also listed, many types of devices that we use in our day-to-day lives. So the next natural question is, what do you actually want from a memory device? What are different characteristics that we look for? Again, same thing. Can the students type out things that they can think of, on the chat? Good storage, less time to retain voltage level. I'm guessing, that probably means like reliability. I mean, you want to store data. Okay. Some of the things that have come out very clearly is, latency. You want fast access to your data. You need high bandwidth. You need low power consumption. Excellent. You need high capacity. Cool. Yeah. So actually, you can think of a variety of these parameters, and unfortunately, no device provides them all. Okay. So in this particular graph, I'm just going to take, let's say, just one dimension, access latency latency and compare it with another dimension, which is cost. I mean, one other thing that we would want is low cost, right? I mean, if we, I mean, if cost were not a parameter, then probably there would be many things that is possible in this world. So here, let's look at access latency versus cost, and then see, we listed a few sort of memory devices in the previous interaction. So let's see how they fall, where they fall in this cost access latency graph, right? So this is what it looks like. So I mean, if typically if you want low access latency, you pay a high cost, right? So on the top left here, you have your processor registers, which are the ones that are extremely close to your CPUs, which give you the lowest latency, but unfortunately, their cost is extremely high. And cost can be in many factors, but here, even if you think of the number of transistors that you have to spend to actually build out these registers, the cost is very high. And as you move to the right, SRAMs give you slightly lower latency. Many of you would have attended the caching lectures. All caches are essentially typically made using SRAM. More recently, they're also. Let me actually pull up. Let's see if I can pull up the laser pointer here. Okay. Yeah. Anyway, so yeah, all caches are typically made using SRAM, but again, SRAM is also high cost in comparison to what we are going to look at today in more detail, which is DRAM. And as you move to the right, on the extreme right, you have your hard drives, which give you the lowest cost in terms of amount of money you spend per bit. Today I can probably buy a 500 GB hard disk for something like $10 or even lower, right? Whereas you cannot even imagine building a 500 gigabyte memory device with just registers, right? So there is definitely this problem where if I go for something that gives me low access latency, I have to pay a high cost. If I go for something that gives me high storage efficiency, then I have to pay a high access latency. So in some sense, all these different parameters that we expect from a memory device, the things that we want to optimize for, they're all conflicting parameters. And today, why do we have DRAM as the choice memory for our main memory? And it is because today it is lying in a nice sweet spot in terms of access latency and cost. Right, and as Professor Madhumutya mentioned, there are some new memory technologies that are coming up, which are essentially challenging DRAM in that particular space. Essentially, DRAM, as we move into the future, may not be cost effective because of various scaling challenges, which we will also discuss in this lecture. Is it fair to compare DRAM? I mean, yeah, I'm also able to see the chat. So if you have any questions, you can just directly post your questions, or even raise your hand and or just interrupt me. Right? Is it fair to compare DRAM and HDD, considering one is volatile and other is not? Volatility is definitely a property that we want from or non-volatility is definitely a property that we want from some memory devices. Regardless, I mean, even if DRAM were non-volatile, the same principles would apply, right? I mean, and it is possible to make DRAM non-volatile. I mean, today the main reason why DRAM is volatile is because it needs continuous power supply, right? And I mean, you can imagine there are designs which essentially convert DRAM into a non-volatile device by essentially pairing it with some non-volatile memory. And even those designs, your access latency for DRAM will be much lower, whereas the cost will be much higher, right? Cost in this graph is essentially, think of it as cost per bit, right? If you want 1 bit of storage in that particular technology, how much are you going to pay? Like it can be, just imagine market cost, right? I mean, today, let's say flash devices like your SSDs and thumb drives, you can probably get it at 1 GB per dollar. whereas let's say a few years ago they were for 1 GB you have to pay like $10, right? So cost is, you can think of it as essentially, the actual market cost of a single bit, right? Anyway, so like I said, DRAM today is in sort of the sweet spot for main memory, and Professor Madhu showed you a real DRAM module as well. So in this particular, and he showed you how this module operates, how the processor interacts with this module in great detail. And in this lecture, what I'm going to do is, there are these 8 chips. I'm actually going to deep dive into one of these chips and understand what happens inside this chip as the processor is sending different commands. It'll also probably answer some of the questions that were raised in the previous lecture, right? So this picture at the bottom that I show here is actually a die photo of a DRAM chip, and you can see those 8. You can distinctly see 8 different boxes here, and within those boxes as well, it's one thing that immediately strikes out is this is a highly regular structure. Right, you can see those grids inside. So essentially, what we will try to do in this lecture is understand, the underlying operation of a DRAM cell. We'll understand how a single cell essentially operates, and then how we will then scale out that operation to get to the microarchitecture of DRAM that we have today. And we will revisit DRAM request scheduling. Professor Madhu covered it in the previous lecture. We will again see how how DRAM actually responds to different commands that are sent from the memory controller. And finally, I'll just today we have seen the DRAM memory module, but there are other form factors in which DRAM is coming up in modern systems. We will look at those other form factors. I'll end with some problems and research areas in DRAM that are there today, and if depending on how much time we take, I will also try and see if I can present some ideas that we have had in the past, on how we can use this understanding of the underlying architecture, to come up with research ideas. I'll give you a couple of examples, and hopefully with that we'll end the lecture. Okay. So what is a memory cell? A memory cell is essentially a physical device that should support 2 operations. So there should be a read operation, and the read will essentially result in a 0 or a 1. And there's a write operation which should allow me to go and change the state of the cell and essentially store a 0 or a 1. Right. This is essentially what we want from a single bit memory cell. Right. And there are many different memory cell technologies that are out there. For example, we can have a cross-coupled inverter. So where I have, let's say, 2 inverters, and I just connect the output of one inverter to the input of the other inverter. Right. This is called a latch. And what happens in a latch? It can be in 2 stable states. Right. So I can either have a 0 state, where I feed the top inverter with the input of 1. So that inverter essentially feeds an output of 0, and this output 0 is fed as input to the second inverter, and that spits out an output of 1, and this 1 essentially goes and feeds back into the first inverter. So essentially, the moment I set this particular device in this 0 state, it essentially remains stable in that particular state. Right? And similarly, the other stable state is the 1 state, where I feed the top inverter with initially feed the top inverter with the input of 0. Right. And there are so this is the inverter latch, essentially shown in a different way, and there are many other memory devices. There is something called an SR latch. There is a level triggered flip flop, and there are edge triggered flip flops. And as you can see, the reason why these things are getting more and more complicated is essentially for speed reasons. So in an inverter latch, to essentially change the state of the inverter from a 0 to 1, I need to force feed this input with a different value, and for the inverter to change its state, it's going to take some time. And as we actually increase the complexity of the circuit with this edge-triggered master-slave JK flip-flop. You can actually go and read about this. This is what is used to manufacture most of our registers. Here, if I change one of these signals, set and reset in the next clock cycle, I'll actually see the result of that in the output here. Right, so they are also designed to work with the clock frequencies of the modern processor. So anyway, so as you can see, depending on what I want out of my memory cell in terms of latency, capacity, I can actually go and design different memory cells just using transistors. Right, but a DRAM cell, as we probably already know, is designed using capacitors. So a capacitor is essentially a device that can store some amount of charge, right? And so here, what I can do is I can actually, maintain it in two states. It can either be in the charge state, or it can be the discharge state. And I can call the charge state to represent a 1, and I can call the discharge state to represent a 0. Right now, while this is good, I mean, this is actually a nice a device that can maintain these two states, which I can use to store a single bit. But there are some challenges in actually using this memory device to actually go and build, or using a capacitor to actually go and build a memory device, right? So what are the challenges? The first challenge is a capacitor is too small, right, to drive any circuit. I mean, the amount of charge that I can store in this can never drive any real circuit, right? There's not sufficient charge to drive current through, let's say, or provide enough voltage for me to actually read data. And the second problem, this again, Professor Madhu alluded to in his lecture, is the read may actually destroy the value. So let's say I'm trying to read data from this charge state. What can happen is the charge may change when I read it, and if the charge changes, then I'm essentially destroying the state that is stored, and somehow I need a mechanism to restore the state of the DRAM cell after I have read from it. Right. So to address these two challenges, what we are going to do is we are going to use the inverter latch that we described in a few slides ago as what we call as a sense amplifier. Right. So let's see how this inverter latch can be used. So we are going to have sort of an enable signal to both these inverters. So what this means is, if the enable signal is true, then the inverters are going to be active, and if the enable signal is false, then the inverters are going to be inactive, right? And in the initial state, so let's say the voltage level at the top was Vx, and the voltage level of the bottom was Vy, okay, and the enable signal is 0, okay. And we are going to, without loss of generality, assume that, let's say, Vx is greater than Vy. So the top is at a slightly higher voltage level than the bottom, okay. So let's say I enable this right now, okay. In this state, I go and enable the inverter. What do you think will happen? Any guesses?
0 to 1, 1 to 0, continuous.
Come again.
Means it will remain at its position. Means 0 will remain 0, 1 will remain 1.
That is true, but here, Vx and Vy are not essentially 0 or 1. There are some intermediate voltage levels, let's say, right? Let's say VDD is 1 and ground is 0, but these are not at VDD and ground. Let's say this is at some level, which is, but what we know is this is greater than this, right? That's all we know, let's say, right? So, okay, so as the name suggests here, sense amplifier, what this circuit is going to do is it's going to sense that, hey, there is a difference between the two voltage levels here, Vx and Vy. And I do know that Vx is greater than Vy. And it's going to sense that difference and actually amplify the difference until it reaches one of the stable states, right? As someone has pointed out here, it will go to one of the stable states, but which stable state it will go to depends on the initial voltage levels. So in this case, we know that Vx is greater than Vy. So what is going to happen is it's going to start amplifying the difference. So the voltage level of this, since this is at a slightly lower voltage level, the voltage level on the top is going to slightly increase to Vx plus delta, and that is going to further reduce the voltage level at the bottom. So it's going to go to Vy minus some other delta, and slowly this difference will keep increasing until finally the top essentially reaches the maximum voltage level, which is VDD, and the bottom reaches the lowest voltage level, which is ground or zero, right? So now in this state, as we described previously, this is going to be stable, right? I mean, this circuit is now stable. This VDD is feeding this inverter. This is feeding a zero here, and this zero is feeding this inverter, and this inverter is feeding a VDD here. So as long as this is enabled, we'll be in this stable state, right? So now let's look at, and of course, if we start with a state where Vx is less than Vy, the top is now going to go to zero and the bottom is going to go to VDD, right? That's the other stable state. So now let's see how we can use this this sense amplifier operation to essentially address the challenges that we described in the previous slide with the capacitor, right? Okay, so this is the setup that we are going to use, right? So this is the sense amplifier, which is essentially the inverter latch that is in the yellow block here, and the yellow block, as we described, as an enable signal, and there's a top wire and the bottom wire. Those are the two wires that are connected to, or you can think of them as the outputs or inputs of the two inverters. And we are going to call this top wire as the bit line. Okay, so this is essentially going to store the state. And here we have, the capacitor, which is essentially the cell that is going to store the charge. And we have an access transistor, which essentially controls whether this capacitor is connected to the bit line or not, right? So we have this transistor, and this transistor itself is controlled by what is called a word line. And if the word line is enabled, it essentially closes this circuit, or closes this switch connecting the capacitor to the bit line. Okay, and like I said, we have the sense amplifier, the enable signal, and the bit line. Okay, so now let's see how we can use this operation to essentially transfer the state of the capacitor to the sense amplifier, right? So the capacitor has two states. It can be either fully charged or fully discharged. The sense amplifier has two states, right? The one state or the zero state, right? Depending on whether the bit line is 0 or 1, right? So let's see how we can transfer the state of the capacitor to that of the sense amplifier. Okay. So initially, what we are going to do is we are going to maintain the word line at 0. The sense amplifier is going to be disabled, and we are going to maintain both ends of the sense amplifier at half VDD, like exactly midway between 0 and VDD, right? So in this state, the first thing we are going to do is we're going to raise the word line, right? And which essentially is pushing that to 1. And once we raise the word line, this essentially connects the cell to the bit line, right? And as you can see, the cell is fully charged, right? So which means the capacitor is at a voltage level of VDD. Now, what happens when you connect something at a higher voltage level to something at a lower voltage level? Then charge flows from the higher voltage level to the lower voltage level, right? So in this case, charge is going to flow from the cell to the bit line, right? So this is going to lower. Obviously, the cell is going to lose some charge, which means its voltage level is going to go down, but it's also going to increase the voltage level on the bit line, right? The bit line has now gained some charge, which means its voltage is going to increase, and so it's going to go to half VDD plus delta, right? In this state, we're going to go and enable the sense amplifier, right? And as we discussed in the previous slide on the sense amplifier operation, the sense amplifier will now detect that there is a difference in voltage levels between its top and the bottom, right? The top is at a slightly higher voltage level than the bottom, and it's going to sense this difference, and it's going to amplify the difference, and it's going to amplify the difference until the top essentially goes to VDD and the bottom essentially goes to 0, right? And this is a stable state, like we discussed, right? So as long as the sense amplifier is enabled, it is going to maintain the state of the top being at VDD and the bottom being at 0, right? Now, as you can see, the cell is still connected to the bit line, right? I mean, this connection is not gone yet. The word line is still raised, which means the cell is still connected, and therefore, as the sense amplifier pushes charge onto the bit line, the charge also flows into the cell and essentially restores the charge on the capacitor, right? Any questions on this operation? This is like this operation is fundamental to how DRAM operates in all memory devices today.
Sir, is there any checking whether the data was read properly?
Is there? There is no check here. I mean, this is sort of this circuit is sort of assumed to work, right? And you know, in most cases, I mean, in the ideal situation where there is no quote unquote process variation, you know, if you go and design this circuit, this is how it will work. There's no need for any further checks.
So as long as the access transistor is turned on, the data from the sense amplifier just directly gets written into the capacitor. So does the memory controller have to anything else to ensure that the data gets written, or it's this on?
Hold on to the question. You know, we will come to that. You know, when we in a few slides from now.
Okay, sure.
I mean, we'll see how you know the memory controller's interaction affects these operations. But you know, I mean, we did say some things were triggered, right? Like the raising of the word line, the enabling of the sense amplifier. Some of these are controlled by the memory controller. Some of these are internally timed by the DRAM itself, right? Okay. In any case, so here, I mean, we started with a cell which was fully charged, and you know, and we saw how after this sense amplification process, the cell essentially returned to the fully charged state. You know, you can again imagine a cell which is fully empty, and if you start with the fully empty cell and you connect that to the bit line, now the reverse will happen, right? The bit line will essentially lose charge to the cell. So the cell will gain charge, bit line will lose charge, which means the bit line will now go to half VDD minus delta, and the sense amplifier essentially take the top to 0, and the cell will again, you know, lose all its charge to the bit line because the bit line is now being driven to 0. So this operation will work regardless of whether the cell is at 1 or 0, right? So what we have done essentially is we have transferred the state of the cell to the sense amplifier. Now, because the sense amplifier, like I said, is in a stable state, I can go and do read write from here. Right? I can read data from this. I can write data back into you know, the sense amplifier. Okay. All right. So now let's look at, you know, so we have looked at the underlying operation of a DRAM cell, and let's now look at, you know, how I might go and build a more scalable architecture out of this, right? So you know, this is a DRAM cell, right? It's pretty small, and so it's just, you know, one capacitor and one transistor. But you know, here, like we discussed, you know, we have the word line, and the word line has to be whether the word line is raised or not for a particular DRAM cell depends on whether I'm currently accessing that cell, right? So I have many cells in my DRAM. When do I decide whether to raise a word line of a particular cell or not, right? And that depends on what address I'm accessing. So I'm going to use the address and some logic, which is in the blue box here, that will determine whether this particular word line should be raised or not, correct? And of course, there is a sense amplifier, you know, which we described, you know, is essential for the operation of the DRAM cell. Now, the problem is that this blue box, the logic in the blue box and the logic in the sense amplifier are both much larger than a cell. Okay. In fact, the sense amplifier itself is 100 times larger than a cell. So I can imagine it's just completely wasteful if I had one sense amplifier for each DRAM cell, right? I mean, actually, that doesn't make sense at all. Then one might ask, hey, why do you even have a DRAM cell, right? You can just get away with the sense amplifier because the sense amplifier itself is a memory cell. In fact, if you get rid of the DRAM cell and just have sense amplifiers, that's pretty close to your SRAM array. Okay. And similarly, this address logic is also, you know, pretty complicated, and you know, it'd be wasteful if you just have, you know, logic that determines whether a single word line has to be raised for a particular cell or not. So to amortize, you know, the cost of these two large data structures, so what modern DRAM architectures do is essentially share them between multiple cells. So I'm going to, as I have shown in this particular figure, so this sense amplifier is not just connected to one cell, but the same sense amplifier is connected to multiple DRAM cells, 4 to be precise in this particular slide, right? Similarly, I will also share my row address or the word line address computation logic across multiple cells. So here, as you can see, each blue box controls not just the fate of one cell, or not just determines whether a single cell is connected to a bit line or not, but it actually determines whether these 4 cells in this row are connected to the bit line or not, right? So essentially, we have a matrix of DRAM cells here, where each row is controlled by the same word line, and each column is controlled by the same bit line, right? right? So so this is essentially what is called a DRAM matrix. So I've essentially compressed, whatever we saw in the previous slide. So as you can see here, we have more packed DRAM cells. We have a single row decoder, which will get in a row address and then determine whether a particular row has to be accessed or not. And then we have this array of sense amplifiers, which are essentially going to talk to some set of cells, right? Let's see, I have a question here. What if capacitor retains some small delta charge? Shouldn't that be read as a zero? Okay. Robin, I'll answer that question in a few minutes after I go through this operation. So let's see how. Suppose I want to access this gray cell, right? Let's see how we might go about doing that, right? So the first thing I'm going to do is I'm going to, essentially, in this case, when I say it's going to be the memory controller. So the memory controller, let's say, wants to read data from this gray cell. It's first going to determine which row does this gray cell belong to, okay? And it is going to issue an activate command to that row, right? This is again, the memory controller operation that Professor Madhu discussed in the previous lecture. And what is this going to do? It is essentially going to transfer. So as soon as I issue this activate to this particular row, the corresponding row address is going to be fed to the row decoder, and the row decoder is going to raise the word line of this entire row. And what this is going to do is it's going to trigger the sequence of operations that I described in the previous slide. So whatever we discussed with a single cell is now going to happen for this entire row of cells. And the data from this cell, the first cell here, is going to be copied to the first sense amplifier, the second one to the second sense amplifier, the third one to the third sense amplifier, and so on, right? So it copies the data from this entire row of cells to this row of sense amplifiers, right? And the second operation is called read, right? Now, when now I know I want to read this gray cell's data. The gray cell is in the third column, so the memory controller will now issue a read to the third column. And like I already discussed before, the sense amplifier is in a slightly more stable state, which means I can actually go and read data from the sense amplifier without worrying about it losing its state. So when the memory controller issues this read command, the DRAM array will essentially read the data from the corresponding column and then send it out to the processor. Right. And the last operation is called a precharge, right? So now, as you can see here, the sense amplifiers are all in the respective stable states, right? And the word line is still connecting these set of cells to the sense amplifier. Now, what if I want to read a different row from this array, right? So let's say I want to read the second row from the bottom. Then I need to sort of disconnect this row from the sense amplifiers and reset the sense amplifiers to that half VDD state, right? From where I can start the activation operation, right? So that's what the precharge operation does. So it essentially disconnects, the precharge operation essentially disconnects the word line. So it essentially lowers the word line. That will essentially mean these set of rows are disconnected from the sense amplifiers. And after that, it essentially resets the sense amplifiers to the half VDD state, right? So a typical DRAM mat will contain 1024 rows and 1024 columns. That's like a 1 megabit DRAM mat. Okay. So I see a few questions. I'll take the questions after I complete this particular part, right? So now this is a DRAM mat, right, which is 1 megabit. 1024 cross 1024, but 1024 cross 1024 is too small, right? I mean, 1 megabit is too small a device for me to use. What I really want in life is, my DRAM module is giving me something like 8 gigabytes or 16 gigabytes. So how do I go and design a 16 gigabyte DRAM from this 1 megabit DRAM mat? So one of the reasons I cannot go beyond let's say 1024 is, as you can imagine, this as the size of this mat increases, some of the cells are going to be further and further away from the cell, and the length of the bit line is also going to be large. As a result, it's going to be difficult for the sense amplifier to operate, reliably if the size of this mat becomes too large, right? So there's actually a size restriction on how large this mat can become, right? So essentially, to create these larger devices, what DRAM manufacturers do is essentially replicate, right? That's the simplest way you can scale out some of these things. So I'm just going to replicate a mat 4 times, and I'm going to call this structure a DRAM array, right? And all these 4 mats are now going to share the same row address. Okay, so the row address that I feed gets shared between all these 4 mats, right? And there's a column selection logic which determines which column to access, that is also shared between all these four mats, right? Now even this is not sufficient. So so here we have a 1 megabit mat, and let's say I have 4 here. Let's say I have 8 mats. That sort of gives me a 8 megabit DRAM subarray. But again, that is also not sufficient. So there is one more level of amortization, which is I actually have multiple. So I have the row address and column selection logic, but I have multiple subarrays stacked on top of each other. And the row address is essentially fed to all the subarrays, and the column selection logic is also shared between all subarrays, right? So this picture here is essentially a DRAM bank where we have multiple subarrays. Each subarrays contain multiple mats, and each mat at the lowest level contains the individual cells that store the data. Right, and I've essentially marked these wires slightly thicker because they are they are indeed much thicker wires, because they have to span this entire length of the DRAM bank, and as a result, the number of wires is also fewer here. Right. So in this particular case, we have 8 megabit DRAM subarrays, and let's say I have 64 subarrays, then that essentially makes a 512 megabit DRAM bank. Right. Now, if I put that DRAM bank into a chip, now suddenly I have 8 banks. Each bank is 512 megabits, and that essentially gives me a 4 gigabit DRAM chip. Right. And if I have a so here I have 8 chips. So each chip is a 4 gigabit DRAM chip. And if I put together 8 such chips, now I have a 4 gigabyte DRAM module. Right. So that's essentially how that's essentially a deep dive into what actually is present in each one of these chips. So let me quickly take some of the questions that have come on the chat here. What if the capacitor retains some small delta charge? Shouldn't that be read as a 0 if you allow noise margins? But here it would be read as a 1. Actually, it won't be read as a 1. So let me see if I can go back to that slide here. So right, so or maybe this slide. So let's say, so here we are starting out at half VDD, right? So let's say the cell has a small amount of charge, right, which is possible. The assumption is that it is less than half. So if the cell has less than half amount of charge, then its voltage level is going to be less than half VDD. And if its voltage level is less than half VDD, then charge will flow from the bit line to the cell. Right. So even if the cell contains a small amount of charge, it doesn't mean that charge will flow from the capacitor to the bit line. It really depends on the voltage level. So if it has a small amount of charge, charge will still flow from the bit line to the cell, which essentially means the top will be, after the charge sharing, the top will be less than off VDD. So off VDD minus delta. So sense amplifier will still take the top part to 0. Right? That's the stable state that it will latch onto. Right. So this operation works even if the cell is not fully charged or the cell is not fully empty, right? So the differentiator here is whether the cell is above the halfway mark. If it is above the halfway mark, it is likely to push the sense amplifier to 1. If it is below the halfway mark, it is likely to push the sense amplifier to 0. Okay. How are row defects handled? So I will maybe take this question towards the end. I mean, obviously there are some cells that can fail to work, some columns that could fail to work. How are these things handled? We can look at it later. Latency also increases when you increase the bit line length. Yeah, absolutely. So latency increases when we increase the bit line length, which is one of the reasons for. I mean, one of the reasons for maintaining it at whatever like this 1024 cross 1024. Right. Reliability is one aspect, latency is the other aspect. Actually, I'll if time permits, I'll take you through a couple of ideas that arise out of the understanding of this DRAM operation.
Sir, following up on that capacitor question.
Yeah.
So you said that capacitor will get charged, right? So what about the next time we read the cell? Wouldn't that be an error as read?
No, if the capacitor will get charged only if you start with a 1. Okay. So only if you start with so in this case, right, only if you start with a fully charged cell, the capacitor will get charged, right? So I'm just going to ask you to imagine. So let's say you start with a 0, right? So when you start with a 0, what is going to happen is the bit line is going to lose charge, correct, to the capacitor. So bit line is going to go to half VDD minus delta. Sense amplifier will now push the bit line to 0. So when I say push something to 0, it essentially means suck all charge out of it, right? So the sense amplifier is essentially going to suck all the charge out of the bit line and essentially pushing it to ground, right? Which means since the capacitor is connected to the bit line, it's going to suck all the charge out of the capacitor as well. So if you start with a 0, you will end up with a 0 here. Does it make sense?
Yes.
Yeah. So if you start with a 1, you will end up with a 1. If you start with a 0, you will end up with a 0. In fact, if you let's say you had a small amount of charge here, right? I mean, it was a 0 state, but the capacitor could have gained some charge, or the capacitor, let's say you start with a 1 and the capacitor lost some charge, right? So let's say it's not full, but it's somewhere 3/4 full, right? But once I complete this operation, right, once I read from the capacitor, it's going to be restored fully, right? So in some sense, the read also restores the state of the cell to its extreme, right? Like either fully charged or the fully empty state. Right. Okay. So yeah, I mean, I'm actually skipping this section on DRAM request scheduling because Professor Madhu has covered it in the previous lecture, right? So let's look at some parameters of the DRAM design, right? Size of the mat, and how they affect some of the characteristics that we want from memory devices, right? So if you look at size of the mat, like I already mentioned to you before, it's going to affect latency, right? If you have a really large mat, the bit line is going to be longer, which means the capacitance of the bit line is also going to be larger, and that essentially increases the latency of access, right? So larger mats essentially mean more higher latency, right? Then we discussed banks, right? So we said there are going to be 8 banks. Now, if you remember from the previous lecture, you can send a request individually to different banks, right? So I can send an activate request to one bank, and in the next cycle, I can send an activate request to a different bank, which means now I am servicing 2 requests in parallel, right? So obviously, if I have more banks, I have more parallelism, right? So that's another property. There is the number of chips in a rank. We saw that in the module that we showed, there were 8 chips in one rank, which is why we got that 4 GB DRAM module. But you can imagine I can put potentially more chips in a rank. Now, if you have more chips in a rank, then you get more bandwidth, because in response to a request, each chip is going to give me some data, right? Each chip is, let's say, going to give me 8 bits of data in response to a request. And if I have more chips, that means for each request, I'm going to get more data, which essentially means more bandwidth, right? In fact, so yeah, we'll discuss some form factors, and of course, we have been predominantly discussing DRAM, the DIMM-based modules in this lecture, but over the years, different application requirements have also triggered various other form factors for DRAM. So let's look at actually a few of those, right? So all of these actually affect cost, right? I mean, you can get lower latency by reducing the size of the mat, right? Very obvious way to reduce latency. But the moment you reduce the size of the mat, the cost of the peripheral structures, so now you need more sense amplifiers for the same capacity. You need more row decoders for the same capacity, which means if you just decide to reduce the size of the mat to reduce the latency, you're going to increase cost. If you increase the number of banks, again, banks, like I showed you, have peripheral structures, right? And those structures, the number of those structures will increase if I increase the number of banks, which means if I want to increase parallelism by simply increasing the number of banks, I'm going to pay a higher cost. If I increase the number of chips, I'm going to increase the bandwidth, but I'm also going to increase the cost, right? And form factor essentially determines, the chip area, chip size, how it is connected, integrated with the rest of the system, and again, those have implications on cost, right? So This is the commodity DRAM, which we have been discussing extensively, and this is sort of the cheapest in the market. I mean, roughly around $5 to $10 per gigabyte. It's used in all desktop, laptop, systems, commodity cloud servers, everything use commodity DRAM, and the fact that this is commodity essentially means that there is not much profit margin for DRAM manufacturers in selling these modules, and as a result, any improvements that we try to make to commodity DRAM to get lower latency or higher bandwidth, it's going to be extremely hard for us to push them to push DRAM manufacturers to actually implement them. Right. Like I mentioned in the beginning of this lecture, we have on-chip caches. On-chip caches are typically built using SRAM. But what we are seeing in more, recent processors is that, caches, we want more and more capacity out of caches, and we also have multiple levels of caches. So while your L1 and L2 caches are still built using SRAM, because their speed is paramount, we want lower latency. But with L3 and L4 levels, we want higher capacity. Right, and as a result, we see that most modern processors actually use what is called an embedded DRAM to build your L3 and L4 caches. So an embedded DRAM is essentially DRAM built on top of a logic die, right? I mean, like directly inside the logic die. And of course, this provides more capacity than SRAM because the DRAM cell is much smaller than an SRAM cell, and it also offers lower latency than off-chip because these embedded DRAMs actually use a smaller match size. Right, the match size here is much smaller, therefore we get lower latency. Right. Many of you may have heard, 3D stacked DRAM. If you follow tech articles. So what is a 3D stacked DRAM? It's essentially a way of increasing DRAM capacity on top of a single chip. So here I have what is called a logic layer, which is the blue layer. And stacked on top of the logic layer is multiple DRAM chips. So each one of these yellow slots or yellow blocks is actually a single DRAM chip, and all of them are connected through to this logic layer through what are called through silicon vias. Right, and the idea behind this is now I can get significantly higher bandwidth at the logic layer. Because in a typical commodity DRAM module, we have a connection that provides you, let's say, 64 bits, wiring, or 128-bit or 26-bit wiring. But imagine the number of wires that you are having connecting this logic layer to these DRAM chips. Right, it's significantly higher than what off-chip memory can provide. So essentially, you get a much higher bandwidth. So examples are, there is high bandwidth memory, which is already in production and commercialized, used by many GPUs and other architectures. There is hybrid memory cube, which is promoted by Intel, which essentially allows for logic, actual computation logic to be present in the logic layer. Right, and applications are like like I said, DRAM cache, or GPUs. Many GPUs use these devices to get much higher bandwidth. So those are some examples of some DRAMs that are present in modern systems. So let's see if I have more questions here. How are SRAMs better than using register banks for caches? Right. I mean, so actually, let me just go back to the slide. So this is your SRAM. This is the basic cell in your SRAM, right? Each inverter is 2 transistors. So you have 4 transistors here, right? This is your register, right? Imagine how many transistors there. Each one is a NAND gate. A NAND gate is 4 transistors. So you have 4 times 8, like at least 32 transistors in this logic, right? And there's also an inverter here, which I'm not including. So the technology size actually doesn't matter here, right? I mean, whether you're at 5 nanometers or 14 nanometers or 21 nanometers, it doesn't matter because with 5 nanometers, I can still manufacture this using 4 transistors, but I need 34 transistors to manufacture this, right? 3D stacked DRAM similar to flash memory. Actually, no. Flash memory actually uses a different type of memory cell, which we have not discussed here. flash memory uses what is called a floating gate device to store data, right? I mean, now that we have gone through this lecture and we have looked at the underlying operation of a DRAM cell, I actually encourage all of you. I mean, there are many memory devices that have come up, right? I mean, as I mentioned in this one, there is this emerging memory technology. There is PCM, there is STT MRAM, there is flash, which has been around for much longer. It's no longer. I mean, we cannot call flash an emerging memory technology. I mean, it's commercialized. It's out there everywhere. So what I actually encourage all of you to do is to go and look at these other memory devices. So when you think of a memory device, try and go into the last level of detail on how is the memory device storing a single bit, right? What goes into storing a single bit into the memory device, and how is that operation scaled up to build the memory device that they're actually selling you. Once you understand that process, you will also be able to come up with potential optimizations, to improve upon it, and that's how research happens in in architecture. You understand things at the lowest level of detail, and that gives you insights about things that you can do differently to improve that operation, or also understand the implications of any other thing that you may be proposing at the lowest level of operation, right? So I mean, in that sense, there have been a lot of, people who don't understand, this DRAM operation at the lowest level. They have proposed many different mechanisms which actually won't work, right? So there have been a lot of such false ideas in architecture, if I may say so, right? So it's very important to understand how these devices operate at the lowest level. So I would actually encourage you guys to, let's say, go and learn about flash memory, right? Like what goes into storing a single bit of data in flash memory, what goes into storing a single bit of data in your hard disk drives, right? And some of these things are fascinating, and essentially help you understand things better. What does Intel Optane use? I think it's a resistive memory. So it's a resistor-based memory where each memory element can be in one of two states depending on its resistance. So it can either be low resistance or high resistance. And if it is low resistance, then it's going to allow more current, and you can detect that. And if it's high resistance, it's going to allow little to no current. And if you can detect that at the other end, you can now store 1 bit of information in that cell, right? And yeah, why is it really useful to speed up systems? So it's actually, so because it's resistance, it's sort of non-volatile. So it essentially allows you to, let's say, get a faster SSD, if I may put it that way. Like it can be used as a replacement for a faster non-volatile device. It cannot replace DRAM. It's definitely slower than DRAM. So you cannot just remove your main memory and put Intel Optane. I don't think it's available in that form factor either. But let's say you can build a storage device that operates on top of PCIe, which gives you much lower latency than your SSDs do today. Right. Okay, so let me actually go through this last part very quickly. So some heavily researched topics. How do we get lower latency with low cost? I think this is a holy grail problem in DRAM. And could possibly become a heavily scaled problem in any other memory technology that replaces DRAM as well. As Professor Madhu mentioned, in the last 20 years, DRAM latency has actually not reduced that much at all. It probably reduced by 10% to 20%, right? And one of the reasons is the fact that DRAM is commodity, and all we care about from DRAM is I want higher and higher capacity. So people have tried everything to ensure that we get more capacity in successive generations of DRAM, but they've not done much to actually lower latency. So there have been some proposals around, but this is still sort of a heavily researched problem. Similarly, how to get high parallelism with low cost. Today we are putting more and more cores on chip, right? And we have multiple accelerators that are trying to access the same memory, which means we are going to get multiple requests in parallel. And it'll be great to have higher parallelism from the DRAM side to be able to service those requests quickly in parallel so that we can get overall better throughput, right? Memory request scheduling is, another. I mean, there have been plenty of papers published on these topics. So in that sense, some of these may be, beaten to death, like or hard to come up with new ideas, kind of problems as well. Someone raised a question. What happens if a thread essentially, let's say, maliciously generate requests such that it keeps its row always open, and therefore keep the memory controller occupied with servicing its requests, right? So there's been a plenty of research that has been done on memory request scheduling and how to improve performance and fairness, by improving memory requests. DRAM refresh. I mean, this is something that we covered. I mean, cells leak charge over time, and if you just leave cells as it is for a very long time, then it is going to essentially remove or change the state of the capacitor, which means you have to periodically refresh, right? And if you have a denser memory, which means if I have more bits in the same area, that means I need more. I'm going to spend more time refreshing data, right? So in fact, this is a super important problem to be addressed in DRAM. It's still an open problem. How do we reduce the amount of time spent in refreshing data in DRAM, right? Because time that you're spending refreshing is a time that is not available to do other memory access, right? Reliability is another big challenge. I mean, as we discussed, the deviation in the bit line voltage is significant for the sense amplifier to be able to detect, right? And if my cells become smaller and smaller, that means my deviation is going to get smaller. If there are cells that are closer, there's going to be more interference. If there is process variation, that is also going to change, change the impact of this deviation on different bit lines. So reliability is another big challenge, right? I think this is one of the biggest scaling challenges in DRAM, to be able to scale it to smaller and smaller sizes, because as this capacitor gets smaller, we're actually talking now tens of electrons being stored in a capacitor as charge, as opposed to anything more non-trivial, right? At a systems level, I think there are again, as I mentioned already in this lecture, DRAM is already present in many different forms in your modern process. I mean, if any of you have a pretty recent laptop, then you at least have embedded DRAM in your on-chip processor. You definitely have commodity DRAMs present, as providing you main memory. Very soon, we may see 3D stacked memory, becoming mainstream to provide you that higher bandwidth. Now, from a systems point of view, if you're interested in operating systems research, how do we manage these heterogeneous memory systems, right? How do I decide whether to store my data in my off-chip commodity DRAM or in my 3D stacked DRAM? This is again, a topic that people are researching. They're looking at it more from the point of view of understanding, how the hardware can manage data transfer between these two things. But I think at an operating systems level, as the heterogeneity keeps increasing, we need more holistic solutions, to address these problems. Right? The other hot area is called processing near memory. As I mentioned to you before, the amount of compute is increasing. I am putting more and more cores, on the CPU, and I have accelerators. I have a bunch of different things, on the compute side, which means the amount of data that I need, that I should feed these devices so that they are busy, is also increasing. But the DRAM channel that connects your DRAM and your processor side is actually not scaling that well. So one of the things that people have considered is actually moving compute closer to memory. So this is typically referred to as processing near memory or near memory computation, a bunch of different names. But again, plenty of research that has happened. But I think it is still an unsolved problem for a variety of reasons. There are questions around what compute to move. Typically, if you look at papers, they consider a very specific operation and say we are going to move this operation to DRAM, but I think that's not going to be very scalable or practical to implement in a real infrastructure. How do we map computation? Like the moment I have this heterogeneous, now I'm introducing heterogeneity in computation as well. How do I write applications that can take advantage of processing near memory if it does exist? how are you going to handle virtual memory? I don't know if most of you are familiar with virtual memory, but most high performance systems manage memory using virtual memory today. And if you have computation off chip and on chip, how are we going to provide consistent access to memory using virtual memory? And again, all processors have caches, which means if I'm manipulating data outside of the chip, then some of my caches need to be made aware of those changes as well. Right. Processing using memory is slightly more niche. This is a line of ideas that I worked on for my PhD thesis, and the idea here is once you understand the underlying operation of a memory cell, the question that we ask is, hey, can we actually use that underlying operation to actually perform more complex operations? I mean, so today we do only read and write. Can I do something more instead of just read and write? Can I actually do copy in DRAM? Can I do bitwise operations in DRAM, right? So there are some niche ideas. These ideas essentially provide significantly better benefits in terms of bandwidth in completing these operations, but at a higher cost, right? I mean, we are going to change the underlying operation of, or we are going to introduce new structures maybe inside of the memory architecture. The key goal here would be to identify killer applications, applications that can significantly benefit from such ideas, and then then lowering the overall cost. Right. All right, so that was this lecture. So let me actually quickly take some questions here. Let's see, where did I leave here? Okay, so Intel Optane, I think we answered that question. Why are we not moving on from von Neumann architecture? It's been a while. What is holding us back? That's a great question. I think we are moving slowly away from von Neumann architecture. And the big challenge is that I don't see a future where all computation happens in an architecture that is different from von Neumann. I think for the foreseeable future, maybe forever, von Neumann architecture is going to be around, and that's because of the general purpose nature of it, right? I mean, imagine just look at what has happened and what the von Neumann architecture has enabled in terms of ease of programming a computer over the past few decades, right? And I think that is here to stay. I don't think that will go away. What will happen is for very specialized applications where we are spending bulk of our effort in terms of the amount of compute that we are spending, the amount of resources that we are spending, those applications may move away from von Neumann architecture. I think a great case in point is deep learning, right? If you imagine deep learning training, for instance, right? It's an operation on which we are spending huge amount of resources, and you already see several architectures that have come up which are not von Neumann, right? No longer the stored program concept where we store the program in some both program and data in a separate device, and then use a centralized CPU to access those instructions and data, right? There we're actually moving to architectures where the program is actually embedded in the hardware, right? I mean, think of your TPUs and other fixed function units that have been deployed for these things, right? Yeah. Okay, so I don't know if I answer the question. I mean, like I said, von Neumann architecture is here to stay, but we will see departure from von Neumann architectures for very specialized applications, right? Yeah. DRAM cell requires continuous power supply, but how to know which cell need to charge at high voltage and which cell does not need to charge? That's a great question, right? So it's a hard problem. So the assumption that we make is that each cell can retain charge for 64 milliseconds, and within the 64 millisecond period, you have to refresh it. And once you refresh it, you're happy. You can assume that it's going to retain charge for the next 64 milliseconds, right? Actually, that's what most architectures today do. And like Professor Muthia mentioned, the 64 milliseconds is also depend on temperature. If you're operating at a higher temperature, then it may reduce to 32 milliseconds. Right? Since all of the DRAM is not really useful is refreshing all of the cells required. Can we not identify which cells are currently used and refresh only those cells? Great idea. I think has been explored to some level in some research papers as well. I would actually suggest just do a a scholar search for DRAM refresh, and you will hit a bunch of different papers which have explored ideas. And I think we are yet to hit ideas that are elegant in the space. And when I say elegant, imagine, so the DRAM space is an extremely weird space, and there's a reason for it. If you look at the manufacturer of DRAM is manufactured by Samsung or your Micron. If you look at the DRAM controller, the memory controller, it is manufactured by your Intels and the AMDs and the ARMs. If you look at people who are writing software for your operating system software, right? It's the open source community that is running writing Linux. There is Microsoft, which is writing Windows, and then there's Apple, which is writing Mac OS, right? For someone to understand which locations of DRAM are actually using useful data or not, you need all people, all the stakeholders in these different ecosystems to actually collaborate and come up with a common mechanism that they will implement, right? Samsung is never going to implement anything inside DRAM until it knows that Intel will follow up on its promise that it will support that mechanism. And Intel will never implement a mechanism until it knows that Microsoft and Apple and the Linux community will essentially implement and use the support that they're building. And today, these big organizations don't care. It's not a big enough problem for them yet to worry about this, right? So any solution that you come up with, as long as that stay within a single layer, right? If can DRAM manufacturers do something within their layer to reduce the refresh time? Can the memory controller do something within its layer? I think those are the type of questions that people are asking today. Or those are sort of the practical approaches that will work today. But there is research in understanding which data is actually used, and then try and refresh only that data. Right. There have been some of the techniques proposed to reduce refresh time in academia. Besides, yeah, I mean, my suggestion. I mean, there's been plenty of work in the DRAM refresh space. I would suggest, and there are papers which have suggested that it's a very hard problem because of this phenomenon called variable retention time. It's called VRT. So let me just type it out here. If you're curious, you can actually go and read up about this as well. So variable retention time is a single cell essentially, retaining data for different lengths of time. I mean, let's say you normally observe the cell, it will be retaining data for like even 1 second, right? So you don't need to refresh that cell for even 1 second, but suddenly there'll be a drop. And it'll retain data only for 32 milliseconds. And people have not fully understood this phenomenon yet. It's not even understood how we can identify cells that exhibit VRT efficiently, so that we can maybe discard those cells or whatever. But yeah, that is something that you may want to look at. Yeah, again, great idea. Sensing temperature and using that to refresh. But yeah, like I said, it's still an open problem, but plenty of research has happened. So my suggestion is go ahead and take a look at literature in that space. Yeah. So yeah, I mean, so since we have run out of time, I'm not going to be able to present the couple of ideas that I want to talk about. But yeah, if there are any further questions, you can just raise now. I think we are entering a break session. I can be around for a few more minutes to answer questions.
Is there any memory models that are used for this computation, like spin-based or?
Yeah, I think that has been one of the challenges. I think people have not yet come up with a. I mean, if you look at, for instance, right? I mean, if you look at GPU, right? You need to write explicit programs and say, hey, this part runs on the GPU, this part runs on the CPU. Right? One can do something similar with processing in memory as well, but there's a key difference between processing near memory and how we use GPUs today. I mean, if you look at how we use GPUs today, GPUs have their own memory, right? And any computation that we want to do on the GPU, we have to transfer the data into that GPU's memory and do the computation there. Of course, I think we are slowly moving away from that architecture. There are, I think, Professor Arka, I don't know if those lectures have already happened. If so, he may have already mentioned, or if you attend Professor Arka's lecture, he may talk about, virtual memory in GPUs, right? How GPUs can be integrated into the virtual memory of the mainstream processor. And so we may need something similar for processing near memory as well. I think the key challenge in processing near memory is, that is the memory that is going to be shared between that is going to be shared by the CPU as well. I mean, it's completely possible to think of whatever processing near memory you're coming up with as a separate accelerator, right? I mean, if you treat that as a separate accelerator similar to GPU, then I think these problems won't exist. But if the processing and if the computation is happening on the same memory modules that your CPU is also accessing, then all these problems crop up. And I don't think there is any clear memory model that has been proposed yet to address these challenges.
Yeah, so just to add to your comment, Professor Arka has not yet covered, so I will be talking about GPUs, where I'll talk about how to
Cool.
communicate GPUs and CPUs.
Sure, great. Yeah, great. Any other questions? All right, cool.
Yeah, looks like we're done.
Yeah.
Yeah, someone.
If we have many modules of DRAM in a chip, so is it need to be communicate between them, or just they will be communicated by the processors to take data?
Can you repeat the question? Sorry.
Suppose we have four modules which you are showing in that chip. So is it required to maintain coherency between them, or just processor will take care of all the things? Means which module we have to go into to take data from that?
So that actually, so there are multiple levels of mapping here, right? So if, your operating system maps virtual address to physical address, and your physical address is used by the processor to do on-chip cache coherence. But when the physical address lands up in the memory controller, right? At that point, the memory controller decides which bits of the physical address map to the channel, which bits of the physical address map to the module ID, which bits of the physical address map to the rank ID, which bits of the physical address map to the bank ID, etc. Right? So you can actually, the memory controller can actually fiddle around with those with those mappings to provide you, let's say, different amounts of parallelism, bandwidth and whatnot. But once the system, I mean, this has to be done at boot time, right? So this is a one-time process. At the boot time, it determines, okay, this is the mapping that I'm going to use to access memory, and it has to use that for the entirety of the life cycle of that particular boot. So the processor doesn't care, basically. It's determined by the memory controller.
Okay, means memory controller will take care of which chip to locate.
Yes. Which physical address should map to which bank and which row and which column. All those things are taken care of with the memory controller.
So memory controller is not just a decoder; it is many more things than decoder. Means it will have some kind of acknowledging unit also should be there. Not only decoder, but there will be some kind of.
Yeah, I mean, like Professor Madhu mentioned, I mean, it is one of the complex components in the processor today, simply because it has to manage many different parameters. It actually has to talk to two different time domains. The processor is running at 3 gigahertz, 4 gigahertz. Your memory system is memory bus is running at a much lower frequency. So there are a whole host of issues that the memory controller has to take into account. So it is definitely a complex system. Yeah.
Okay, sir. Means that timing difference is also taken care by that memory controller.
Yeah, everything is taken care of the memory controller. Yeah.
Okay, sir. Thank you, sir.
When the load is followed by a store operation to the same location, can this be exploited from the microprocessor to save recharge time? Actually, like I said before, whether you do a load or a store, you'll restore the data, right? So it doesn't matter. So in fact, if I just read from a particular row, I am actually refreshing the data of all the cells in that row, correct? Because the restoration process will essentially take it to the extreme, like I mentioned, like fully charged or fully empty, which means we can actually avoid refresh to a row which has recently been quote unquote activated. But how now it's an idea. Like how do you make it practical? I mean, like I said, if you go and read the literature, there are already papers which try to do that. Let me actually try and see if I can pull up some of those papers. There's something called elastic refresh. Techniques to mitigate refresh penalties in high density DRAM. Yeah, I mean, like I said, maybe I can. Let me see if this opens up the paper. Yeah, this is like a decade-old paper. And like I said, there are definitely many more recent papers. Something called Radar that comes to mind. There is Smart Refresh, I think, which is the one that which tries to implement the idea that you're proposing, which is, hey, if I've just read some row, then I don't have to refresh that row. Right. Any other questions? All right. Yeah. Thanks for attending the lecture.
Thank you, Dr. Vivek, for the interesting and interactive lecture. If there are any other questions, so I request all of you to please note down, and then we have a doubt clearing session. So I request Dr. Vivek to also to be available if possible.
Yeah. So actually, I was going to mention that I may not be available at 4:30 today. So you do have my email address. So if there are any questions, just feel free to send me an email.
Sure. So I'll consolidate and send you.
All right. Yeah. Thanks a lot, Swiss. Thanks everyone. Yeah.
Thanks. Okay. So we have a break right now, and then we'll come back at 12 o'clock. So please keep attending the sessions. Thank you. Bye then.